Alright, so we're going to take a closer look at L'Hopital's rule, and specifically other types of indeterminate forms. So we're used to using L'Hopital's rule when we have the indeterminate form 0 divided by 0, or infinity divided by infinity. And we were fine if it were plus or minus infinity at that. However, there are other types of indeterminate form that we've kind of avoided thus far. 0 to the 0, there's 1 to the infinity, there's infinity minus infinity, or 0 times infinity, or infinity to the 0. So these are all other forms that are indeterminate, like we can't get an answer when we get something in this form. It just doesn't work that way. So we need to find a way to somehow simplify it so that it does work. And what we're going to do is learn how to make those indeterminate forms into the ones we know how to work with L'Hopital's rule. So for our first example, we're going to evaluate each of the following limits. So for example A, we're going to find the limit as x approaches infinity of e to the negative x times square root x. Okay, so we're starting with one that hopefully is a little obvious of where we're going to take this. So in its current form, this causes a problem for us because we basically would end up with 0 times infinity, which is one of those forms we don't have as much experience with. So we're going to try to rewrite it. And luckily, since we have a negative exponent, I hope you're thinking what I'm thinking. Let's rewrite it as the limit as x approaches infinity of square root x in the numerator. And we're just going to bring this e to the negative x down to the denominator. So that then what's really happening is that we're really going to end up with an expression that looks more like infinity divided by infinity. Now, I will warn you, on the AP exam, they expect to see it written in this notation. They do not, as tempting as it is, they do not want this to end up anywhere on your paper, because to them that's not a mathematical statement that's possible. And I know that seems kind of weird, but they're strict about it. So instead, when you're working through these problems, make sure to kind of set your work up on the side or beneath and use a bracket, and then say that's how we know use L'Hopital's rule. Okay, because we're seeing that we get infinity over infinity. So now from this point on, it's like what you're familiar with. So we're going to take the derivative of the top and the derivative of the bottom. So for the top, don't forget that this is really like x to the 1/2. So when we take the derivative with the power rule, the 1/2 comes down and it leaves us with x to the negative 1/2. So it just leaves that square root in the denominator of that piece. And then the derivative of e to the x is simply e to the x. Now before coming to the side and showing my work for this, I kind of like to clean this up if I can. So it's a complex fraction, so I'm going to rewrite it as the limit as x approaches infinity of 1 over 2 square root x, and then that's just going to be pulling this guy into the denominator, so times e to the x. So we can see here it's not possible to get another indeterminate form because we have 1 in the numerator. So at this point I can simply evaluate the limit, and it's definitely going to be 1 over something growing really, really large, which will simply result in 0. Alright, now for example 1, part B, we're going to have the limit as x approaches 1 from the right of 1 over ln x minus 1 over x minus 1. So again, don't ever write this as part of your answer, but kind of your scratch work, so to speak. You could notice that this would turn into infinity minus infinity, which is a problem for us. And so we want to rewrite this somehow so that we can end up with infinity over infinity or 0 over 0. So for this problem, I'm thinking our plan of attack has something to do with this minus sign. Like we don't really want two separate terms for L'Hopital's, we want one term. So I'm going to try to find a common denominator to write instead of two separate fractions. Okay, so we're going to multiply this guy over here and this one over here. So I'm going to end up with x minus 1 minus ln x. over their common denominator of ln x times x minus 1. Alright, so if we find the limit as x approaches 1 from the right of the numerator, x minus 1 minus ln x, that's going to be 1 minus 1, which is 0, minus ln of 1, which is 0, or 0 minus 0, which is 0. And if we do the denominator of ln x times x minus 1, as we approach 1 from the right, again, that's going to approach 0 times 0, which is 0. So here we're getting that 0 over 0, and I'm going to be lazy here and abbreviate L'Hopital LH. That's the indeterminate form we're familiar with, so we can just move forward from there. Okay, so we've got to derive the numerator first. So we're deriving x minus 1, that's just going to become 1, minus the derivative of ln x, which is 1 over x, all over the derivative, we've got a product, so we're going to have to do product rule. So first times the derivative of last, which this, again, would just be a 1 if we derived it. So first d last plus last d first, and then the derivative of ln x would be 1 over x. Yikes, okay. Let's try to just clean this up before testing L'Hopital's rule one more time. Sometimes it doesn't make a difference, but sometimes it does, so I like to check. So the numerator, this piece right here, we could simply rewrite as, I'm just going to do this because it's going to get messy. So that's going to become x minus 1 over x times the denominator right here. How can we make this prettier? Well, the way it's currently written, we would have x ln x plus x minus 1 all over x. And then I need to multiply by the reciprocal of that here. So I'm going to get x ln x plus x minus 1 with an x in the top. Alright, so we can clean up at least this guy, can cancel out, which means that we're left with trying to find the limit as x approaches 1 from the right of x minus 1 over x ln x plus x minus 1. So now I can finally see if we need to do L'Hopital's rule one more time. So we're going to end up with the limit as x approaches 1 from the right of x minus 1, which is definitely going to give us 0, and then the limit as x approaches 1 from the right of x ln x. So ln of 1 is 0, so that whole piece will become 0, plus x, so that's 0 plus 1, and then we subtract 1 again, so this is still giving us an indeterminate form. Okay, so we got to do it, hopefully not more than once, but yeah, we'll find out. So we're going to take the derivative of the top. That's going to make me happy because the derivative of the top is just 1. So we're definitely not going to have to do it again because that's a constant. Now the derivative of the bottom does not make me as happy because it's going to involve a little bit more work. Alright, so I did the product rule here. First d last plus last d first, and that's this part here. The derivative of x is simply plus 1, and the derivative of minus 1 will become 0. Now we can finally do something. So these basically are going to counteract each other, and I can just plug in a 1, and I'm going to get 1 over. These guys right here just canceled out the x's and left me with a 1. ln of 1 is 0, and then the plus 1 gives me a 2 in the denominator. So 1/2 is our final answer. Alright, so this concludes your notes looking deeper into L'Hopital's rule. We'll continue this in class tomorrow with some examples of how natural logs sometimes also have to be used with L'Hopital's, so I know you're excited for that. But yes, anytime we get indeterminate forms that aren't 0 over 0 or infinity over infinity, we must do some algebra to get them there first, so that then we can still utilize this rule.